We perceive the number line as a smooth, continuous surface, but that unbroken appearance is a mathematical illusion. Beneath the surface, the number system consists of highly rigid, nested mathematical sets. Every number fits into a specific mathematical taxonomy, categorized by absolute and unbending structural rules. These rules dictate the number's behavior, determining how a decimal expands or whether a value can be fractured into smaller units. By building this system from an absolute void, we can observe how discrete, separate units forge the continuous real number line. Mastery of mathematics requires an analysis of the structural DNA of numbers rather than their surface values. Before any system exists, there is only a mathematical void. This foundational layer is the set of natural numbers, represented by the symbol n. These are the counting numbers, used exclusively to quantify discrete, whole entities. Even at this basic level, numbers are categorized by their internal factors, the whole numbers that multiply together to create them. Prime numbers are natural numbers greater than 1 that possess only two factors, 1 and the number itself. Composite numbers are natural numbers greater than 1 that possess more than two factors. However, this set cannot describe the absence of quantity. It lacks a representation for nothingness. Adding 0 to natural numbers creates an expanded set known as the whole numbers, or W. While we can now represent 0 and positive totals, the system remains structurally unbalanced, extending in only one direction. This set is effective for basic counting, but it is structurally incomplete because it lacks mathematical symmetry. A number system only accounting for positive accumulation cannot describe debt or opposing direction. To solve this, we must introduce mathematical symmetry to the line. The rule for opposites dictates that every number must have a counterpart located the exact same distance from 0 on the opposing side. In this model, 5 reflects across the 0 anchor to create -5. Combining these negative whole numbers with the existing whole numbers creates the set of integers, designated by the letter z. 0 serves as the immutable anchor for this set, acting as its own opposite. This establishes our first containment hierarchy. Since every natural number is also a whole number with a positive sign, the entire natural set is contained within the integers. The integers provide a perfectly symmetrical framework, but they leave infinite empty structural voids between each and every numerical coordinate. If we zoom in on the line, we find vast unquantified spaces existing between the integers. Rational numbers, or Q, are the structural tools used to fill these gaps. To be classified as rational, a number must be expressible as a fraction of two integers. This rule has one absolute constraint. The denominator can never be equal to 0. This fractional definition determines exactly how the number behaves when written in decimal form. The first valid behavior is termination. The decimal 0.75 is rational because it ends completely. The second valid behavior is repetition. A decimal that repeats a specific pattern infinitely is also rational. All integers are technically rational numbers because they can be expressed as fractions over 1. Consequently, the rational set entirely swallows the integers, further expanding the mathematical hierarchy. Rational numbers populate much of the line, yet microscopic, rule-breaking fractures remain hidden in the gaps. Even with millions of rational fractions, the line is still not perfectly solid. Tiny gaps persist. These spaces are occupied by numbers that defy the fractional rules of the rational set. These rule breakers are classified as irrational numbers. An irrational number is defined by a decimal form that never ends. Furthermore, these decimals never repeat in a discernible pattern. Pi and the square root of 2 are the most common examples of this chaotic profile. Despite their complexity, irrationals still obey the rule for opposites, resulting in values like -pi. Because they cannot be expressed as fractions, these irrational anomalies exist completely outside the rational hierarchy. To create a truly continuous number line, we must combine the nested rational sets with the separate irrational set. This unified collection is known as the real numbers, or R. The real numbers represent every possible point on the infinite number line, finally eliminating all gaps. We can verify this taxonomy by tracking the number 4, which qualifies as a natural number, an integer, a rational, and a real number. Pi, however, bypasses the inner nests. It is excluded from the rational set and exists only as an irrational real number. The unbroken continuity of the mathematical world is made possible by the strict, non-overlapping axiomatic rules of these hidden taxonomic sets.